The paper introduces a novel approach to address the issue of small subgroup-wise sample sizes in regression discontinuity design, RDD, a widely used method for causal inference under intervention determined by a continuous variable. Hierarchical regression discontinuity design, HRDD, is proposed as a hierarchical Bayes method that estimates subgroup-level parameters of treatment effects and assigns a hierarchical prior distribution to borrow strength from other subgroups. This approach solves the problem of highly unstable estimation results due to limited sample sizes in each subgroup. HRDD employs a pseudo-model based on a quadratic function for estimation and utilizes Gibbs sampling for posterior computation. The optimal bandwidth can be automatically selected using Hyvärinen scores for unnormalized models. The proposed HRDD demonstrates improved stability in point and interval estimation compared to separately applying the standard RDD method to each subgroup, as shown through simulation and real data analysis. The paper discusses the background of RDD, its wide adoption in various fields, and its limitations when estimating treatment effect heterogeneity over subgroups. It highlights the scarcity of effective methods for pursuing treatment effect heterogeneity under RDD and emphasizes the need for a new approach to address the issue of small sample sizes. HRDD is then introduced as a solution to this problem, leveraging hierarchical Bayes techniques to borrow strength from other subgroups. The paper explains the key features of HRDD, including its pseudo-model, Gibbs sampling for posterior computation, and automatic bandwidth selection. The authors also discuss the advantages of HRDD over conventional RDD methods, particularly in terms of providing more stable point and interval estimation results. The paper concludes by summarizing the contributions of HRDD and its potential applications in various fields. It emphasizes the importance of considering subgroup treatment effect heterogeneity in RDD and suggests that HRDD can significantly improve the accuracy and stability of such analyses. This research paper introduces a novel hierarchical Bayesian approach to estimate subgroup-wise treatment effects in clinical trials. The proposed model is robust and efficient, handling outliers and borrowing strength from other groups when sample sizes are small. It utilizes a two-component mixture distribution for potential outliers, ensuring robustness against outliers while maintaining efficiency in posterior inference. Hierarchical prior distributions for the treatment effects and regression coefficients across different subgroups allow for stable estimation of subgroup-wise treatment effects by borrowing information from other groups. An optional spike and slab prior is suggested for the treatment effects, effectively shrinking them towards zero when they are close to negligible. The paper outlines a strategy for posterior computation using conditionally conjugate priors for the unknown parameters. This approach facilitates efficient sampling from the posterior distribution, enabling researchers to draw inference on the subgroup-wise treatment effects and other model parameters. The proposed method is designed to be flexible and adaptable, accommodating various choices of weighting functions and kernel functions, and providing a robust framework for estimating subgroup-wise treatment effects in clinical trials. The research also discusses a hierarchical model for Bayesian inference in linear regression, introducing a novel prior distribution for the regression coefficients that incorporates latent variables to model uncertainty. The model is defined by a set of equations and algorithms for Gibbs sampling, detailing the steps for generating parameters. The prior of tau g is conditioned on a latent variable Sg, which is sampled from a Bernoulli distribution. The model includes a hierarchical structure for the prior of pi, with parameters of pi and b tau. The paper highlights the efficiency of the proposed method for Bayesian inference in linear regression, particularly in handling uncertainty and providing a flexible framework for modeling complex relationships. The authors extend the proposed hierarchical regression discontinuity design, HRDD, to accommodate binary responses, enabling the estimation of treatment effects in a wide range of applications with categorical outcomes. They adopt a logistic model for the conditional probability of YIG, given by P, YIG equals 1, tau g, beta g, equals express, micro ig, 1 plus express, micro ig, where micro ig equals tau g wig plus zig beta g. The treatment effect tau asterisk operator G is defined as the difference in the expected values of YIG when ZIG approaches the cutoff C from the right and left, respectively. To estimate the treatment effect, the authors employ a pseudo-model based on a weighted log likelihood, given by P, YIG, tau G, beta G, proportional express, micro Ig YIG KIG, 1 plus express, micro Ig, KIG. This pseudo-model reflects the influence of local information around the boundary of RDD through KIG. The authors assigned priors to tau G and beta G, and utilized the polygamma data augmentation to develop an efficient sampling scheme for estimating the pseudo-model. The posterior computation is carried out using a simple Gibbs sampler, which involves sampling from the polygamma distribution, and then sampling from the conditional distributions of tau G, beta G, and other hyperparameters. The adaptation of bandwidth is crucial for robust decision-making in the context of regression discontinuity design, RDD. To estimate the subgroup-wise bandwidth parameter Hg, the authors propose using the local Hyvärinen score, which is a function of the bandwidth H. The score is evaluated based on the leave-one-out pseudo-predictive distribution for the out-of-sample observation, pH, YIG, Yi, G, which is not necessarily normalized. The local Hyvärinen score can be expressed as the sum of two terms: the expectation of the second derivative of the log predictive density and the squared expectation of the first derivative. The expectations are taken with respect to the marginal posterior distribution of theta Ig. To estimate the optimal bandwidth, the authors propose an iterative algorithm, referred to as the local selection, which updates the bandwidth parameter Hg based on the Hyvärinen score. The algorithm starts with an initial set of candidate values for Hg and updates the value based on the score computed using a small batch of MCMC iterations. The authors also consider a global selection approach, where the common bandwidth H is selected based on the average Hyvärinen score across all groups. For binary responses, the authors use a modified definition of the Hyvärinen score, which is based on the predictive distributions pH, 1 YIG, Yi, G, and pH, YIG, Yi, G. The local Hyvärinen score is then defined as the sum of the squared ratio of the predictive distributions and the ratio of the predictive distributions. The authors note that the predictive distributions can be expressed as integrals with respect to the marginal posterior distribution of theta Ig. The research proposes a hierarchical regression discontinuity design, HRDD, to estimate subgroup-wise treatment effects in clustered samples with continuous response variables. The method incorporates group-specific random effects into the regression discontinuity design, aiming to provide robust estimates. The authors define the local Hyvärinen score for selecting the optimal bandwidth parameter, which is used to evaluate the performance through a simulation study. The results demonstrate that HRDD outperforms separate regression discontinuity designs, SRDD, and standard RDD in terms of bias and coverage probabilities, especially in scenarios with outliers or skewed error distributions. The application of HRDD with global bandwidth selection, HRDDG, is shown to be particularly effective, offering stable and accurate point estimates with significantly shorter credible intervals. The findings suggest that HRDD is a superior method for estimating treatment effects in such scenarios, especially with global bandwidth selection. Here is a combined summary of the 4 pages. The research compares the proposed hierarchical response data distribution, HRDD, with conventional separate methods under binary response. 9 scenarios of data generation were simulated, and HRDD was applied based on the logistic model, alongside separate RDD, SRDD, using the RD-robust package. Both methods were evaluated for optimal bandwidth, local linear regression, and quadratic regression for bias correction. Results in Table 2 demonstrate that HRDD provides more efficient point and interval estimation than SRDD. An empirical study of the Colombian scholarship program was conducted, focusing on subgroup treatment effects by gender, socioeconomic status, SES, education levels of father and mother, and school type. The analysis identified 106 subgroups with small covariate proportions around the threshold, resulting in a total sample size of 274,251. Both HRDDG and HRDDL were applied with spike and slab priors on groupwise treatment effects, along with SRDDC and SRDDBC. In the analysis of the Colombian scholarship data, the RD-robust package was utilized to estimate treatment effects for each subgroup. Results indicate that SRDD methods produce numerical errors in 6 groups, possibly due to small sample sizes around the thresholds. Subgroup-wise bandwidths used in HRDD methods in these groups were replaced with the average value of the subgroup-wise bandwidths in other groups. A scatter plot comparing the estimates of SRDDC and HRDDG shows that the estimates of SRDDC are highly variable and unrealistic in some subgroups, exceeding a value of 1. Figure 3 presents the point estimates and 95% credible intervals of the treatment effects for all 106 groups, obtained by HRDD. The estimates are around 0.25, exhibiting a certain heterogeneity among subgroups. The top 3 groups with the largest treatment effects are identified, and the lengths of the 95% credible intervals are reasonable, with all credible intervals bounded away from 0. The research paper presents a general framework for estimating subgroup treatment effects under the sharp regression discontinuity design using a hierarchical Bayes formulation. This framework allows for the estimation and comparison of treatment effects across different subgroups, addressing the need for more flexible and robust methods. The authors discuss potential extensions, including fuzzy RDD, quantile treatment effects, and incorporating other measures of treatment effects. The paper also provides an overview of existing literature on RDD, highlighting its limitations and challenges. Additionally, it references key works in the field, including studies on robust nonparametric confidence intervals, quantile treatment effects, and the use of regression tree models for causal inference. The authors emphasize the value of the proposed framework in addressing the challenges associated with estimating subgroup treatment effects under RDD and acknowledge the potential for future research.